이걸 이제 켜주시겠어요? 지금 아니면
네,
이미 켜져 있는
저기
건
선이 연결 안 돼 있어요.
아, 그러면은 지금 화면이 어느 화면이 나오는 걸까요?
확장된 것 같습니다. 오른쪽에.
그러니까 확장이 되어서 어느 쪽이나 제가 여기를 쓰면 똑같은 거죠. ED9은 똑같을 것 같은데. 하고 이렇게는 맵핑을 1번 모니터로 바꾸고 자, 그러면 봅시다. 제가 지금 눈이 잘못된 건가요? 왜 이게 원래대로라면 스케치와 관련된 스케치북이 있었던 것 같은데.
그 펜 모양 말씀이시죠?
네네. 이게 어디로 갔을까요?
약간 안 되겠다. 검색 기능에서.
네네. 그렇게 해볼게요. 여기 원래 검색 기능도 여기 창에나 있었던 것 같은데. 뭔가 좀 다. 여기 원래 검색창이 있어야 되지 않나요?
그러니까 그 윈도우. 네네. 윈도우
그냥 치면 나오는 거.
그거는 그냥 화면 캡처였습니다.
그냥 이렇게 하면 쓰여지나요?
네, 이거는 지금 그 화면 캡처.
네네. 그건 알겠어요. 근데 캡처를 하고 빈 화면을 캡처를 하고
네.
그다음에
검색이 윈도우 아닌가요?
그냥 윈도우 키 누르고 치면 노래 나와요.
오케이. 시작하시죠? 네. 오케이. one strange thing is actually it should be copied. So let me just do that and display. Okay. Now it seems that it works. Okay, so before today's lecture we've done up to lecture 13. After that we took certain Q&A session, so Q&A, and now we are in lecture 14. So as I understand, so all of you succeeded to have the convergence solution for your DC simulation, and yes, so if you have a certain points which is not implemented yet, then please have your time. So okay, so this is the second half of our semester. So in this semester we will go beyond the contents of our computational microelectronics book. So beyond our textbook we will go further. And so I think that since we have a lecture 2 days per week, so we have Monday and Wednesday. So my suggestion is, so here we have just 2 days term, yes. And
Tuesday.
oh, okay, so okay, Tuesday and Thursday, because I have because I have 2 lectures, 2 courses in this semester, so a little bit confused. Anyway, so between these 2 days we have 2 days term, and yes, here we have 5 days term. So I will assign relatively simple homework to you for this term, 2 days term, and we'll go to more advanced homework to you, so in this 5 days time. Okay, so today is just Tuesday, so we will have a relatively simple homework. So I will just tell you how can you do that. So now if we have to consider the contents of the last contents of remaining lectures, I have to say in this way. Up to now, we have discussed about DC simulation. More or less, we have considered how can we implement on a 2-dimensional structure, and drift diffusion was the most important thing you have to implement. So I think that all of you have done it successfully. So now we will go to advanced simulation technique beyond the DC simulation. Of course, all of them, those analysis technique are well known for a long time. So even 25 years, all of them were available. However, even nowadays, actually, it is not that easy to find certain information about the analysis beyond DC simulation. So that's the reason why in the remaining semester I will talk about how can you do those analysis. So the first thing we will consider is obviously transient simulation. However, transient simulation will be extremely simple. So you will find that that is so simple. After that, we will move to AC simulation. So the reason why we first cover the transient simulation is transient simulation is the general one. So that can consider most general waveform of our input signal and output signal. So that is the general one. However, this is not very much efficient. So in terms of efficiency, it has a certain disadvantage. So that's the reason why people have invented so small signal analysis. So that is small signal analysis. So we will learn about this. So we will consider this type of analysis. After that, we will move to noise analysis too. So this is related with Mr. Piran's work in our laboratory. Also, I think that it is partially related with also Mr. Park's research work these days. So in order to have access to this kind of analysis, yes, we have to have these intermediate steps. But please note that although our ultimate goal will be noise analysis or green function and related statistical approaches, something like that. However, each of them, transient simulation and AC simulation, yes, so each of them is more important, even more important than this final one. So this is really specified and narrow scoped analysis, and transient, this is the most general one we have to learn, and we will go to further and further specialized and variable analysis technique. Okay, so I see that when I was a PhD student, my major was this one. So my major research work was the calculation of a green function and application to the noise. So in order to achieve this goal, we have to learn about almost every simulation technique available. So I just wanted to teach you or introduce you those techniques. So I think that after this semester, you will learn almost every simulation technique related with transient behavior. So hopefully that will be very helpful for you for your future career. Okay, so then now let's come back to our transient simulation. Transient simulation itself requires certain kind of time derivative. However, as I told you before, so a few minutes ago, so we will just concentrate on simple homework because this is just Tuesday. So what I wanted to ask you to perform is now you can calculate the DC IB characteristics of your double gate MOSFET. So okay, some of you cannot yet, but I hope that you can do it quite well with a short time. So my suggestion is now just to mimic the behavior of transient simulation. So think like this. So usually gate terminal is regarded as input terminal and drain is regarded as output terminal. So what I want to ask you is just to draw and consider this case. So up to now you have done it. So if we take the semi-logarithmic scale, then you will find that this looks like this. Yes, this is your answer about my homework. But now think about this case. Yes, instead of VZ as a x-axis, so now we will just consider time. Yes, and time. Let's just assume, for example, this is a kind of microsecond scale. So let's say that, for example, starting from 0, you move. So for example, up to 1 microsecond, your gate voltage is just kept as 0. So then what will happen? Since your gate voltage is just 0 and your transistor is now turned off, so hopefully you can guess that yes, in this case maybe my ID would be close to 0. So after that, let's assume that from this 1 microsecond your voltage suddenly goes up to what? Up to your VDD. So what is your VDD? So which value was used for your simulation?
1 volt.
1 volt. Okay, so then let's assume that you have just applied 1 volt, and of course it is not very convenient to apply this kind of abrupt transition, so it's not possible actually in reality. So instead of that, so consider certain transition time. So for while, let's just make it simple as possible. So let's just say that from 1 microsecond to microsecond, your voltage linearly increase. So starting from here, yes, so you will have a slope corresponding to what? So slope corresponding to, for example, your gate voltage will increase by a rate of 1 volt per 1 microsecond. Yes. After that, your voltage is still kept as VDD. After that, yes, so this time scale is, let's just make it simple as possible. So now 3 microsecond, and now at 4 microsecond in this time scale, now your signal goes to 0. Okay, so now sorry about ugly drawing. Okay, yes. So now let's think about this case. Now you have applied a pulse to your input terminal. Yes. Now your voltage previously biased to 0 was suddenly goes to 1 volt. After that, after short duration, so it comes back to 0. So what will happen? For a short time period or time interval, like just 1 or 2 microsecond, there will be certain measurable current. So otherwise, you don't have any meaningful current for your drain terminal. Okay, so now my suggestion is, as a homework 14, please simulate this case. However, we have not discussed about how can you actually simulate the transient behavior. So please adopt such kind of quasi static approximation. So it means that although the signal itself varies as a function of time, however, internally inside your device, you don't care about the transient effect. So always, when you just have 0.5 volt, for example, 0.5 volt, then in reality, if we really consider this transient behavior, your system have to consider the previous status of your system and the current bias voltage. So these two factors will determine your current status. So are you with me? I mean that the status of right now is given by, here we have our history and present input. These two factors will determine the present status. Okay, so I mean that, for example, yes, here we have a relatively slow change of our voltage, but instead of that, why don't you just consider 1,000 times steeper transition, for example. Yes, for example, let's just say that 1 volt is changed from 1 microsecond to 1 microsecond plus 1 nanosecond. So then you will have 1,000 times faster transition. So do you expect the behavior of your system is the same with these two cases? So actually not. You will have such kind of a transient effect. So means that although your two cases share the input, the same input, like increase in voltage and finally go to, for example, 1 volt. However, depending on the history, the way of your lamping or the rate of your voltage lamping, your present status at the end of this lamping will differ. So that is the general case, but today I'm not asking you perform this full transient simulation. Instead of that, let's assume that your output is just fully determined by only by your input. So how can you achieve this kind of situation? Simply just to perform this simulation. So in some sense, this kind of terminology like quasi-static approximation is a kind of word to justify your laziness. So if you are lazy, so you don't want to consider time transient effect, then you just solve the DC and you just name it as the quasi-static approximation. Simply, quasi-static approximation means that you neglect the time derivative of your system. So that is simple one. So what you have to do is, now you have the example input signal. Yes, now you have it. Then please keep your please keep your VD value as VDD. So it will be just 1 volt. Yes. Now you apply this waveform, input waveform for your system, your double gate MOSFET, then you will have the ID as a function of time. Of course, the waveform. Yes. So if we have time and if we have ID, then actually the waveform can be immediately obtained from your ID versus VZ curve, because you have, for example, you have 0 volt, then your current is fixed. Yes. And if you have 1 volt, yes, you have also predefined value from your DC simulation. Also here the same, and also here you have the same. So internally, maybe your current will just looks like this, increasing in this way, not a linear way, but you have a certain margin. For example, let's say that up to here, up to your threshold voltage, your device will not conduct at all. Only after the threshold voltage, then your current will increase. So you will have non-linear behavior of your ID as a function of time. But please note that inside this analysis, no transient effect is involved. Everything is just obtained from ID versus VG. So then what you have to do is not like this. If you do it in that way, this is the way I will explain from now on. That is a long implementation. For example, okay, since this is really quasi-static, so first calculate DC simulation. So make a table between ID and VG. Then after that, take this waveform as an input and just draw this ID. Yes, that will give us the real solution, but the solution is the correct, but please think about the reason why I give you this homework. This homework is prepared to have the exposure to transient simulation eventually. So in the case of real general transient simulation, you cannot build a table like this. So ID can be obtained as just a function of gate voltage. No, in general, it should be regarded as a function of time only. So it's not possible. So instead of that, please proceed in that way. For example, yes, here we start from this time zero. First, prepare the time zero solution. What is the time zero solution in this case? Since gate voltage is 0, yes, at the beginning, and drain voltage is 1 volt, first perform the DC simulation. So just DC simulation up to Vg equal to 0 volt, so you don't have to lamp it. So however, you have to lamp the drain voltage. So this can be done with your DC DC simulation. So please prepare your first initial solution. So after that, let's do it together. Now you have the long time to proceed. For example, at least you have to perform your simulation at least 4 microsecond long, or for example 5 microsecond long. So yes, so when you have the domain, simulation domain, what you do in the device simulation is just to discretize it. So when you have, for example, your transistor, yes, this is your transistor for double gate MOSFET. What you do is just to introduce a certain number of points, and after that you just discretize the equation on the mesh generated from this set of points. So natural approach for even this time axis, yes, here we have time axis t, will be just to discretize the entire time domain. So for example, from 0 to 5 microsecond, let's just to use, for example, 0.1 microsecond differences between these neighboring discretized time instances. So then how many time points will occur? So there will be 51 time instances. So if you do it really straightforward, then what you do is, for example, let's say that you have 1000 mesh points, spatial mesh points, the mesh points inside this two-dimensional system. And if you have 51 time instances and just make the global unknown variable vectors, for example, let's think about this one, then you will have a huge vector, and it will have 5, 5, 5 at a certain position, and also certain time 0, time 1, time 2, blah blah, and at the end of this vector you will find certain quantities corresponding to t sub 50, the last time point corresponding to your time here. Oh, then previously when you perform the DC simulation, more or less you needed, for example, 3000 unknown variables, because we need 3 unknown variables for them, 3 different types: potential and electron density and hole density. And let's assume that there is more or less 1000 mesh points. Then total size of your Jacobian matrix would be 3000 by 3000. However, if we just expand our simulation into the transient domain, then we have to consider multiple time instances And when we consider them all, then yes, depending on the number of discretized time points, the size of our Jacobian or size of unknown variable vector becomes just becoming explosive. So 50 times larger one. So that is really too heavy. So we are curious about why we have to spend a lot of computation resources on that point. Of course, it is because we have to consider different time instances. So that is not that much unreasonable. However, anyhow, it is not that good from the viewpoint of numerical efficiency. We wanted to avoid solving this huge system as much as possible. So that's the problem. Okay, then maybe you can ask me, okay, if we have 51, then the size will be, yes, this number, and since we have more and less 3 points, we'll just have roughly just 150,000 unknown variables in it. So it's not that much. We can solve it. Yes, you're right, but this is the under assumption of 1000 match points, and usually the typical number is not 1000. Typical number is 10 or 100,000 mesh points in it. And please note that since we are considering only one cycle or one single pulse, the number is just 51. Think about the full operation of NAND flash. So in the NAND flash, you have to test your device, for example, write and erase, write and erase. So that should be repeated because you have to test the robustness of your NAND cell. So you will do several periods, so full period of your operation, and you have to observe what happens to your system. So simply speaking, both of them, so spatial dimension and temporal dimension, these numbers, my example numbers, are far too underestimated. So if we have to consider the realistic case, yes, the numbers really becoming really huge. So it's not really desirable. So please note that even the DC simulation is just manageable to us. So we don't have much room for even bigger simulation. So please guess that, assume that the DC simulation is at the border of our computational resources. So beyond that, maybe it would be very difficult for us to simulate that system. So simply speaking, this kind of approach, so think about spatial dimension multiplied by our temporal dimension, that approach cannot be used at all. So of course, if you ask me, is there any approach really using this kind of multiplication? There is such kind of application. So this kind one, number of spatial mesh points and number of discretized time instances, so make a really grand unknown variable vector and make a grand Jacobian matrix and solve them all simultaneously. That really exists. That approach is typically called as harmonic balance simulation. So harmonic balance simulation, of course the name sounds quite weird to you at the first time. So the name harmonic balance comes from different context, but anyway, in the case of a harmonic balance simulation, you can just put all of your unknown variables into grand Jacobian and just to solve that problem. Of course, in reality, harmonic balance, inside it we make a certain kind of transformation. But anyway, the basic uh, basic philosophy is just to consider both of our spatial dimension and temporal dimension in a equal base. So why do we care about the time axis in a special way? Just to treat it just like spatial dimension. So we just to discretize our four-dimensional system. Yes, we have a three-dimensional real space, and as a fourth dimension we have a time, and just like our two-dimensional or three-dimensional space, we just discretize our time and try to solve them all. However, as you know, harmonic balance is typically very efficient or very important for certain problems. Certain means that some specialized problem. For example, if you are talking about the distortion of your RF devices, then this harmonic balance simulation is really important, and you have to perform this harmonic balance simulation. However, in general case, I think that most of your application would be just memory devices or logic devices, and not RF device. If then we need a more general approach. So please come back to this our discussion today. So now I hope that now you understand this approach, just considering the time, just like spatial dimension x and y. That is not very easy because too heavy computational burden. So then what we have to do is, instead of considering time as a spatial or certain additional axis, please concentrate only on the current value. For example, like this. So let me just explain. Now you have the initial solution. Then I want to ask you, where are you now? Where are you now? Now you are at t equal 0. This is the current situation. Then instead of considering all of your time scale from 0 to 5 microseconds, just to concentrate on your first time. So focus on your t equal to, for example, 0.1 microsecond. Then once you focus on this spatial time instance, then what you get is, okay, since time is 0.1 microsecond, now our gate voltage as a function of time now becomes just 0 volt. Okay, now d equal to time, that is always kept as 1 volt. Then please try to solve this simulation with this condition. Of course, you will find that, oh, there is no difference between step 1 and step 2. The bias is not changed at all. Yes, but please just do it. Then what will happen? You will have the immediate convergence because you have already the solution. So when you just try to solve your system further once again, so your Jacobian matrix and your Newton iteration will tell you that, okay, we are already at the solution, you don't have to solve further. Okay, it's good. Then let's move to the next step, t equal to 0.2 microsecond. So what will happen? Once again, just try to evaluate gate voltage and drain voltage. So then you will have the same message once again. Oh, that is quite tedious. But let's go to the our 11th step. Then what will happen? So 11th step, now t becomes 1 microsecond. Yes. So Vg is still, yes, just 0 volt. Vd is as always 1 volt. So nothing happened to your calculation. Then please go to the next one. The next time point, it is corresponding to 1.1 microsecond. Then please guess what will happen to your gate voltage. So what will be the value? Of course Vd equal to 1 volt. So now we here. Now we are here. Yes. So here 1.1 microsecond, and this time interval is divided. This time difference is divided by 10 time intervals, 0.1 microsecond, and voltage difference is also given by 1 volt. So yes, we will just have 0.1 volt as a voltage here. Yes, 0.1 volt. After that, please solve this system with your DC simulator. So then, of course, you can say this way. Okay, every DC simulation requires the initial guess. So then, for this step 12, what should be the initial guess? In this case, please just assume that the voltage difference between two neighboring time instances is not that large. So just to keep the solution, and please try to your current situation. So be with me. So now you can do it. For example, maybe you can have some difficulties. For example, when you try to just jump from gate voltage equal to 0 to 0.1, or maybe your simulation can fail. If you have such kind of components of failure, then please reduce the time differences. Instead of this one, yes, for example, you can try 0.50 nanosecond. So 2 times shorter time difference. Then okay, up to this point everything will be just straightforward, no actual solution. After that your simulation will go to, for example, 1.05 microsecond, and your target voltage for your gate voltage will be just 0.05 volt instead of 0.1 volt. So to your device simulator, maybe 0.1 volt can be too difficult to job, but you know 0.05 volt, anyhow it can try. If it fails even in this case, okay, then just stop. Then please reduce the time steps. Then just controlling the time step, obviously you will have a smaller voltage step. Then anyhow eventually you can get certain reasonable value of time differences between your time. Okay, so now let's assume that, for example, a lucky case like your 1.1 microsecond solution is obtained without any numerical difficulty. You have the converged solution. Then what will you do? Go to the step 13. Then now your t becomes 1.2 microsecond. So then what will happen? Gate voltage becomes 0.2 volt, and Vd is still 1 volt. So by doing this job, you can get the solution for this lamping period without any difficulty. Okay, the point is just take the previous solution, the solution at the previous time instance as your initial guess, and under the assumption of a sufficiently fine discretization of your time axis, you will have good convergence behavior for your this quasi-static transient simulation. Okay. So after that, now let's assume that now you have achieved or arrived at this point. So maybe you will have a step 21. After that, you will have 10 more iterations or 10 more time steps, and you will go to 31. And in this case, maybe your simulation will be also very easy because you don't have to actually change your solution. So you have the solution, and your code will say, okay, you have the solution, so let's go to the next one. You will go really quick for this period. After that, you have the downhill. So starting from this 31 up to 41. So now your time increase. Now you will have lower and lower voltage. So starting from your 1 volt as the initial value, initial guess, now you have to solve the case of 0.9 volt, 0.8 volt, and 0.7, something like that. So in this sense, you are not ramping up your bias, you are now ramping down your bias voltage. So anyway, you can do it. So after all of your simulation result, of course, at the end of every successful step, of course, you have to measure your ID. So you have to measure T0, and for example here you have to ID at T12 or something like that. So then you will have after long simulation with 51 time steps, then eventually you will have a vector containing ID at 51 time instances. Then just draw it as a function of your time. So now you have the time because you set those time points, and now you have the numbers like this. Then you will get certain numbers or certain waveform like this. That will be the transient simulation. So of course, I have to say that this is not actually transient simulation. It is long, but we are just mimicking the general transient simulation. Of course, inside it we are using just a conventional DC simulation, nothing new. So we are just doing the DC simulation. But I wanted to ask you just to transform your current code built especially for just DC simulation to the code which is more suitable for general transient simulation. Okay, so of course the next topic, the next lecture will be just to include the time derivative terms into your system. Then eventually you will get real general transient simulator. But before doing that, just to make the framework. So although your analysis itself is quite much quasi-static, however, at least you have the tool which can generate your output as a function of time. So that is the intention I give you this homework. Okay. So do you have any question about the homework problem 14?
그러면 시간은 그냥 제가 임의로 설정을 하는 거고 그 볼테이지에 따라서 제가 직접 바이어스를 걸어줘서 그 결과를 출력하고
Yes, you're right.
저런 펑션의 커브를 그리는.
You're right. So this LED curve shown here, or LED waveform shown here, usually this curve itself is not given by developer. So the application, so if you are working with a NAND flash, then actually the timing of your NAND flash determines that waveform. If you are working with DRAM and DRAM, or if you are working with the logic technology, then the operational frequency of your system will determine that one. Or even you are working with, for example, power device or RF device, at domain specific or application specific timing will determine the behavior of your waveform. Yes, that's true. But point is, the application just to specify the continuous waveform for your simulation and how many points should be placed in your waveform in a discretized sense. That is not much specified. So, for example, if you can simulate your system with only 1, 2, 3, 4, 5, 6, let's assume that you can achieve the converged solution for converged solution with only 6 points. Is it good enough, or that is too bad? In my opinion, if you are working with non-linear circuit elements, then you do not have to perform like a 6 points, 6 time instance simulation, because inside this lamping period or this lamping down period, or even this plateau, so you will have a lot of time transient effect. So you have to have reasonable resolution on your system. So simply speaking, the number is not determined by the application, but you have to care about them. Not too many, not too small. So if you just have just a countable of 1 over 2 or 3 over 4 numbers for each period, then your simulation will be really crude. So you cannot believe it. That's a good question. And another comment on it is, for example, think about our typical example like a sinusoidal signal. If you have a sine or cosine as an input signal of your voltage, then how many discretized time instances are required for discretizing one single sinusoidal point? So, for example, if you just introduce 4 or 5 points, then you will have this behavior. Then are you happy with this 5 or 4 points per period? Okay, maybe not. And you have to have, for example, if you spend, for example, 100 points, then you will have a lot of points in it. Okay, you will like it, but that is really related with the increase of your simulation time. So compared with this 4 points case, if we introduce 100 time points, so roughly speaking, we have to have 25 longer simulation time for our one period simulation. Of course, I have to say that if we apply 100 time points or even higher number, then maybe 2 neighboring time instances are so closely populated, so our Newton iteration will take just 1 or 2 or just a small number of iterations. Although in the case of 4 points, so we have to jump into from 0 to 1, 1 to 0, 1 to -1, and -1 to 1. So that will take a lot of even not diverse, then we will spend a lot of iterations for each step. So the exact ratio will be not like 25, but anyway, it's true that if you perform final time steps simulation, then usually it is related with the increase of your simulation time. So please to have reasonable number of points for your time in your time axis, but not try to make it so dense. That is, in my opinion, too that is not a smart practice. So you have to be smart enough to control the time steps. Okay? So from this discussion, now it becomes really clear that you have to adjust the time distances or time differences between two neighboring time instances. However, the purpose of our course is not teach you every detail or every tricks, but just to introduce the technique in a general introduction. So just to consider uniform time differences. But please note that in reality, commercial or any serious transient simulators have a certain capability to check whether we can further increase or the time steps or not. So simply speaking, let's think about this first period, okay? Or not first period, but this first phase here, starting from 0 to 1 microsecond. Actually, you have nothing. You have the solution, and you don't have to spend your time for simulating this one. However, although you understand that is just meaningless, but your simulator itself, your code cannot recognize it, or your code cannot anticipate that, okay, eventually I will have the meaningless simulation for 1 microsecond. So what we can do is just to take the number of iterations. For example, at the beginning, starting from step 1 to 2, step 2 will have just one single iterations for getting the converged solution. Number 1, the number of iteration 1 is really remarkably small number. It means that already we have the solution. So it strongly indicates that, okay, we are quite close to the solution. So then, from this consideration, your simulator have certain courage. Okay, maybe I can go to more aggressive. So instead of this 0.1 microsecond, maybe if it has a certain adaptive routine, it can go with, instead of this step 3, it can go to step 3 dash, like t equal to, for example, 0.2 something. How can it justify its behavior? There is no actual justification, but from the history, from the current behavior, maybe this system is not that much deviated from the current situation. So maybe we can try to save our time by increasing the time differences, not 0.1 microsecond, but increase it to 0.215 microsecond. Of course, what will be the reasonable value? For example, 0.2, 0.3. Obviously, in this case, the best value will be just 0.9. if you can find 0.9 second, 0.9 microsecond as your increased time difference, then that will be the optimal one. However, nobody knows. Nobody can understand the best value will be 0.9 microsecond in advance. So what we have to is instead of having too ambitious about finding out this optimal value in one shot, just continuously increasing the value like 0.15. Okay, then what will happen? In this case, it will be a great success. Okay, even when I increase the time difference from 0.1 microsecond to 0.15 microsecond, it works. Then maybe it is now getting further increase. So now, instead of this guy, maybe if we can try, for example, this number. So what will happen? In this case, our delta t becomes 0.225 microsecond. We just increase the time difference by factor of 1.5. Why we have used 1.5? It is because previously we have also used 1.5. The difference was 0.1 microsecond, but in this case 0.15, it works. So now increase it further. Okay, then what will happen? Still, this step 4 dash will perform perfectly. Oh, great. Then the next one will be what? So then now this one is further increase, and yes, maybe what will be the values? 0.3375 microsecond maybe. Yes, then let's just add them. Then we will have about t equal to what? 0.8125. So I'm not quite sure my calculation is correct. But anyway, we will have such a number. So what will happen? Yes, still we will have perfect agreement. Then let's go to, here we have some problems. Let's go to number 6 dash. Oh, good. Then let's go to the next part. The next part will be just once again increase factor of 1.5. So delta t will be now 0. What should be? It would be around 0.5. So sorry about that. I have no ability to calculate it exactly. But let's say that 0.5. So then now it will try, for example, 1.3 microsecond. Then what will happen? Obviously, it will suffer from convergence problem because suddenly it tried to solve. So previously it solved around here, okay, up to here. It looks perfect. After that, it just jump into this part because up to now everything was so smooth. So yes, just to go ahead, increase the time steps. But now it has the hard hit about the convergence problem, or now it says, oh, something is wrong. Then I have to cut back. So usually, how can it cut back is, okay, previously I tried 0.5 microsecond. So now just to come back to 0.1 microsecond. Okay, that is too much. So instead of that, usually we use a factor of 2. So just coming back to, for example, 0.5 microsecond. Then what will happen still? Now in this case, the time t would be not like this. T would be 1.05 microseconds. Okay, then now you feel that yes, maybe it can solve it because the the gate voltage will be just 0.05 volt. So we are around here, so it can be achievable. So then we can solve it. Then now we have reasonable number of Newton iterations. So now it detected, oh, the number is not, the number of iteration is not like 1 or 2. So it means that we are more or less just normal iterations. So maybe it is not very easy or wise to increase time step. So when your Newton iteration get the convergence almost immediately, then please try to increase your time step. And if your Newton iteration just converge, for example, if you say that I will wait for 12 Newton iterations or 15 iterations or 20 iterations, that is they are usual numbers you take in realistic simulation. Then if your simulation is converged, however, that number, the number of iteration is quite close to the limit of your endurance, then please do not increase the number, or please do not increase your time step. That is not a wise approach. So just to stay there, and only when you have 1, 2, 3, 4, oh, compared with my preferred number 12 or 15 or 20, that number is so short, so maybe we have some rooms to further increase our time step. So that is actually adaptive time control. And this adaptive time control is not the invention of the ticket guys. Actually, this problem is actually obtained from the circuit simulation guys. So like a SPICE. So in a SPICE, they have to also consider the time distances. So you know that this kind of simulation, applying certain input signal and getting the output signal as a function of time, is not only done by device simulator, but also it is done by circuit simulator. In some sense, it is more heavily used in the circuit simulator. Circuit simulator is always try to solve huge system, which is composed of several SPICE models, like PSIM or something like that, compact models, and they try to solve it. So to them, this adaptive time control is really critical. So they have even further emphasized on this adaptive time control, but I think that for our purpose it is enough to just mention like this way. So adaptive time control can be done, and in the device simulation, the time control is more or less based on the number of Newton iteration for previous time step. But in the case of a circuit simulator, they have invented even more elaborated measure to take the time difference or control the time differences. But in my experience, so in the case of device simulation, usually, although if you have looked at the manual of commercial device simulators, you can find a long discussion about how can we, there are many different options to control the time differences. So if you are really getting rigorous, then you can put this control method, another time control method, then that will be very good in terms of accuracy. But you know that, please keep in mind that Transient simulation is extremely costly, so that is really expensive one. Compared with the DC simulation, it requires more time steps or more iterations to get the full output signal. So of course it is more valuable. So DC simulation is just a DC, but transient simulation gives us some full information about system behavior. So that is more valuable, but in some sense that is sometimes too expensive. So more and less device engineers try to cut the simulation time as much as possible. So that's the reason why they are not that much rigorous about controlling the time steps. So just to monitoring the number of Newton iterations, and if the number of Newton iteration is small enough, then they believe that, oh, my simulation is quite close to the solution, so maybe we can increase it. Okay, so do you have any question about today's lecture? So, however, I'm not asking you to implement this adaptive time control. So this is beyond the homework. So please just use the uniform time discretization. But point is, so you have just 2 days or 1.5 days. So please try to implement this quasi-static transient simulation. That will be quite helpful for your future homework program. Okay, do you have any question? Okay, then now time is up. Now let's just stop here.